Problem number 5. On a digital calculator display, the number 2011 can be read upside down as 1102, 1102. Whereas 2007 cannot, since digits like 3, 4, and 7 cannot be read upside down. Starting with 1, the fifth number that can be read upside down is 8, and the 15th is 21. What is the 2011th number that can be read upside down? Alright, well, this is the type of calculator display that I'm thinking of. It's a 7-segment display that you see quite often on simpler calculators. I think some of the graphing calculators have a more detailed display, but this it's a display that just uses 7 segments and lights up different segments to represent numbers. And you can see that, if I were to turn these numbers upside down, a 0 looks like a 0. Okay, this one is just, I've just rotated this display here. So a 0 looks like a 0, a 1 looks like a 1, a 2 looks like a 2. But when you turn the 3 upside down, it looks like an E. So that one, even though it looks like a letter, it can't be read as a number. Okay, so so any numbers that contain a 3, when you turn it upside down, you're not going to get another number. All right. The same way with 4. 4, when you turn it upside down, it kind of looks like a lowercase h, and so it's not a number. So that one, when you turn it upside down, won't look like another number. 5 looks like a 5. 6 looks like a 9, but it still looks like a number. So that's okay. We can read it when we turn it upside down as a number. And 7 kind of looks like an L. It doesn't look like a number, so we'll cross that out. 8 looks like an 8, and 9 looks like a 6. But that's still a number, so that's okay. So we essentially have 0, 1, 2, 5, 6, 8, and 9 that look like numbers. Okay, so we have 7 of them. 7 digits that look like numbers. And so I'm actually going to show you a couple different ways to do this. One was the way that this probably would be more common, and another one that's a little simpler, but it requires probably a little more experience with with math. It's a little bit of number theory, a little bit of base number stuff. So let me do the way that I did it first for you. I'll do that. I wanted to take a look at these numbers by decade. I'm going to say this is by decade, this is by century, and this is by millennium. Okay, so I've just grouped them in 3 different ways here. So if we look at the numbers by decade, well, we know anything that contains a 3 in the units digit is not going to be read upside down. Okay, we're not going to be able to read it upside down. Same way with 4, the same way with 7, right? So for each row, we have 7 numbers. But then when we look at the tens digit, then again, the 3s can't be read upside down, the 4s can't be read upside down, and the 7s can't be read upside down. So in each decade, we have 7 numbers that can be read upside down, but the decades that start with 3 and 4 and 7, none of those can be read upside down. So we have 7 decades with 7 numbers each, so we have a total of 49 numbers in the first 100 numbers that can be read upside down. Okay, and you might notice that I started with 0 here. That's kind of important to note, because when they say to do the counting, it says start with 1. Okay, starting with 1. So even though this kind of looks like the first digit, I'm kind of disregarding it. I'll have to remember to disregard that at the end. Alright, so for each century, we have 49 numbers that can be read upside down. So, and then the centuries that have a 3, or a 4, or a 7, can't be read upside down, right? And so we're going to have 49 numbers per century that can be read, and we're going to have 7 centuries that can be read, okay, because we've eliminated 3 of the centuries. So 49, oops, I corrected this one, 49, 49, 40, 49, 49, okay. So 49 times 3 ends up being 343. All right, this is essentially 7 cubed. This is 7 squared. So we're going to have 343 numbers per century that can be read upside down. And then if we look at the numbers by millennium, so we know this is 343, and we can't read the 3000s or the 4000s or the 7000s upside down. So we have 7 millennia that can be read in 343 numbers per millennia. Okay, so we end up getting 7 times, or it'd be 7 to the 4th, which is 2401. Okay, so if we were to add up all of the numbers all the way to 9,999, we'd have 2,401 numbers. But we've gone past the number that we're looking for. We're looking for the 2011th number. So we've gone too far. So the question is, where do we end up? If we have 2011 numbers, where does that put us as far as the millennium? So if we take 2011 and we divide it by 343, then we'll end up getting 5, which is 1715, with a remainder of 296. All right, remainder 296. Okay, so that tells us that we're going to go through 5 full millennium and 296 more. All right, so 1, 2, 3, 4, 5 full millennium, and 296 more is going to put us here at the 8,000s, okay, because we have to skip the 7, right? So this is the first millennium, 1, 2, 3, 4, 5, skip the 7, that's supposed to be crossed out, and so we end up at 8. So we know that the thousands place of this number that we're looking for is an 8, right? Right, because we're going to be somewhere in this 8,000s millennia. 296 numbers into that. So where are we going to be in the century? Okay, we've got 49 numbers per century. So let's take our remainder. We know we're at 296 numbers into it. So we take our remainder and divide it by 49. So we have a remainder of 296. And if we do that, we actually get 6. That's 294 with a remainder of 2. All right. And so that means that we're going to be through 6 full centuries plus 2 more, right? So 1, 2, 3, 4, 5, 6 full centuries. So we're going to be in the 900s. So this was our thousands place. 9 will be our hundreds place. All right. So we have a remainder of 2, so we're going to be 2 into another decade, and 2 more. Now this looks like it's going to put it at 1, but we have to remember that we started with 0, and our problem told us to start counting at 1. So 1 is the first number, 2 is the second number. And if that's the case, then that puts us at 2. So we don't go through any full decades, and then we have 2 more. Okay? So this is our answer, 8,902. All right. Now, if you know something about counting in different bases, so what I'm talking about are like counting in binary. A lot of people know how to count in binary because that's a useful one. It's used in computers. But let's say we were counting with only 7 digits, which is essentially what we've got to work with here. Right? If I scroll back up here, these are the digits we have to work with. We can't use 3, 4, or 7. So essentially we're counting with 7 digits. Now, even though, so this is our 0th digit, this is our first digit, this is our second digit, this is our third digit, so our third digit is 3, or sorry, our third digit is 5, I should say. Our fourth digit is 6, our fifth digit is 8, and our sixth digit is 9. So, okay, so we have 7 digits, 0 through 6. Okay, so normally when we count in base 10, we just use the same, or sorry, when we count in base 7, we normally just, for simplification, just use the symbols, the same symbols that we use in base 10. But it really doesn't matter. These are just symbols, okay? I could count in Japanese, or I could count in Greek, with Greek letters. I could call this alpha, and then beta, and gamma. It doesn't, these are just symbols, okay? So essentially what we're doing is using 7 digits, counting using 7 digits. So an equivalent question to what we're being asked is, what is the 2011th, oops, hang on, 2011th number, 2011th number in base 7, okay, where we're using only 7 digits to count, okay, we're using these digits to count, okay, and an equivalent to that would be, what is 2011 in base 7, okay. And when we only have 7 digits to count, now I'm going to go back to counting the way we typically do in base 7, which is just to use the numbers 1 through 6 and 0. We use those 7 digits, okay? And then we'll have to match it up to what those digits actually are, okay, according to this, because 3 corresponds to 5, 4 corresponds to 6, 5 corresponds to 8, okay? So we're using different symbols, but I'm just going to first of all use the normal base 10 symbols and count in base 7. Okay, so in base 7 what we do is, our units digit just counts how many ones, just like in base 10. Okay, so we're going to count, 0, 1, 2, 3, 4, 5, 6, and then we run out of digits. We don't have, in base 7, we don't actually have a 7. Okay, so then the next number after that is going to be 10. So this place value here, okay, this is the 1's place. This is actually the 7's place. So that keeps track of how many 7's you have. And then once you have, you get up to 66, again, you run out of digits. And then this place value is going to keep track of how many 49's you have. Okay? And then once you get up to 666, you run out of digits again, and this is going to keep track of how many 343's you have. Okay, so this is 7 to the 0, 7 to the 1, 7 to the 7 squared, and 7 cubed. Alright, so so the question is how to represent 2011 in base 7. Okay, so what we can do is just divide it by 7 and figure out how many 1's we're going to have. Alright, so if we divide that by 7, so this is 2, 14, 61, let's see, 8, 56, that's 51, and so, what is it, 6 times 7 is 42, so, 7 times 7 is 49, and 2 left over, okay? So we can actually group 2011 into 287 groups of 7 with two